So let's discuss section 12.2, problem formulation. So this is the case, okay, like a discrete time, linear time invariant system, okay, the same system like before. Then X is state, omega is the process noise, okay. Then the process noise is assumed to be zero mean white Gaussian noise with covariance matrix Q is positive definite. The initial state x0 is also zero mean Gaussian with covariance matrix pi 0. It's positive semi-definite. And we assume the initial state is independent of the process noise for all k is greater or equal to 0. Then the only difference here, we use a wireless sensor network. Okay? Instead of a single sensor, here we use n sensors to measure the state, to estimate the state xk. Then for each sensor, it has the measurement equation. So in this form. And here it consider a case that the sensor is like a sense scheduling problem. So each time we can choose to activate the sensor or not activate a sensor. Okay. So the gamma here is a random variable. So gamma ik is a random variable. So it can be equal to 1 or 0. Okay. So if the gamma I is 1, it means the I sensor is activated. When gamma ik is 0, it means the I sensor is not activated. Then it said that when the sensor is activated, so the sensor can measure the system state and also can exchange its estimate, okay, with its neighboring sensors. So when gamma ik is 0, so the I sensor can only receive estimates from its neighbors. So it cannot share its estimates with the neighbors. So here, so yik will be the measurement. So you see when the sensor is not activated, so the measurement will be just 0. Then bik here, so it is the measurement noise. It is zero mean white Gaussian with covariance matrix RIK is positive definite. We also assume the measurement noise for other sensors, okay, they are independent. And also the measurement noise is independent of both the initial state x0 and the process noise for all k. So that's basically the problem formulation. Okay, so it's like a stochastic scheduling problem. Okay, so the gamma ik here, so it is IID is IID random variable. So IID it means independent identical distribution. Okay. So it means all gamma ik, they have this, they all independent, okay? And they have the same distribution. Then we can consider the gamma k is a Bernoulli distribution, okay? So it's when gamma ik is 1, so its mean is q. So when gamma ik is 0, so its mean is 1 minus q. So I mention again, so the all gamma, the all random variables. So gamma I, omega k, bik, and x0, they're all random variables. So we assume they are mutually independent for all the sensors and for all k. Then to model the sensor network, we can use a dirichlet graph. with the vertex node. So each vertex, okay, V will just represent the sensor. So we have n sensors, then we index the sensor from sensor 1, sensor 2, and sensor n. Then we have the edge. So edge will be a subset of two-element set of B. It means the communication links between them. Okay. So if in the set E there is ij, so it means the sensor I can receive information from sensor J. Okay. Then we can define the set of neighboring sensors of sensor I. Okay, this means all sensors, it can share information with sensor I. Okay. Then we denote DI with cardinality of the set, the neighborhood set, and I. This will be just a number of neighboring sensors of sensor I. And here to assume the graph is strongly connected. Okay, that means it contains a direct spanning tree. Okay, but in graph theory, it's called spanning arborescence. Okay, in graph theory, we do not call it a tree. Okay, so that means there's a root. It can send information to all the other nodes in the sensor network. Then at least for this section, I think this assumption, it doesn't matter, at least for this section. Okay, I don't see the necessity to use this assumption. Okay, then the result in this section still hold if the sensor network is not strongly connected. Then when we recall that the I sensor cannot share information to its neighbors. Okay, if the sensor I is not activated at time k, then in this case we have a subgraph. Okay, so it means the graph gk at time k. Then we can define the Laplacian matrix. So it in this way. Okay, it's just a subgraph. Okay, for the original graph G. Okay, if there's a link. Okay, if sensor I can receive information from sensor J, so it also depends on time k if sensor J is activated or not. Okay, even though there's a link, if sensor J is not activated, so here it will be 0. Okay, so if sensor J is activated, then we have -1. Then the Laplacian matrix is same with the Laplacian matrix of the original graph G at this location, the ij location. Then the diagonal entry of this matrix, Laplacian matrix, will be the row sum. Okay, okay, the ith row. Okay, you take all the off diagonal elements, then add them together, then put a minus sign. Okay, so that's the Laplacian matrix. Then otherwise, we define the entries will be at 0. Okay, so here is the distributed state estimator at the ith sensor. Okay, then it's very similar to a classic Kalman filter. So except at this part. Okay, so this is a prediction part. For second part, when sensor I is not activated, so the second term will be 0. Okay, so only prediction, no corrections. Okay, so only when the sensor I is activated, then you have the second term. Okay, it's like Kalman filter. You have the prediction, then you have the correction using the measurement YIK. Then to consider sensor network, there is a third term. So third term, it can be considered as a consensus term. Okay, so you want to use your neighbor's information. But the question here is, if this structure, the optimal structure for distributed state estimator, then I think we need to put a question mark here. Okay, it's not sure. Okay, if this is the optimal structure. Okay, then in this section, so we assume the estimator is in this structure. Okay, it may not be optimal. The structure may not be optimal, we assume it is in this structure. We want to find the optimal K. Okay, so that is the goal in this section. Okay, then first of all, we have to mention that so this filter, okay, may not be optimal at the first place. Okay, here we only want to find the optimal K given the structure of the estimator. So we assume the initial estimate for the state is 0. Then the epsilon 0 will represent a coupling string. Okay, it's referred to as the consensus gain. Okay, so assume in the range, so 0 and 1 over delta will be the maximum di. So di we defined before is the number of neighboring sensors, okay, of the ice sensor. Then you take, so you find the sensor with the maximum neighbors, okay? So that will be the range for epsilon. But here again, at least at this section, it's not clear why epsilon must be in this range, okay? So it's not clear. We're not sure, at least in this section, okay? Then we want to find the Ki, is estimator gain. Okay, we want to design the Kik by minimizing the mean square estimation error. Okay, the one-step prediction. Okay, so that's the error. Okay, so from K, we want to predict K plus 1. That's a true state. Then we take expectation. Okay, so the mean square estimation error. Then the expectation is taken over all random variables. Okay, the process noise, measurement noise, and also the random variable to control the activation of each sensors. Then the estimation error will be defined in this way: the estimate state minus the true state. Okay, then we can use a simplified notation. Okay, then here the calculation is straightforward. Okay, we just take the equation from the state estimator and the equation, okay, from the system. Then you have something. Also, you need the equation, okay, of output. Then you will have some form like this. Okay. Then for convenience, you can define Fi as A minus gamma I K Ki Hi. Okay. Then based on 12.5, okay, then you can calculate. So here will be the E transpose. Okay. So mean square estimation error. Okay. Then the calculation is straightforward. Okay. So here is the covariance matrix of the estimation error sensor I and estimation error sensor J. Okay. So the calculation is straightforward. You just use 12.5. Then something I would like to mention that, so here it contains some errors. Okay. Because it does not include the cross term. Okay, so when you multiply the EI and EJ, there should be some cross term between VIK and omega K. Okay, then you see you cannot find such term. Okay, but it will not affect the final result. Okay, because when you take expectation, then the V and omega K, they're independent. Okay, then they have zero mean. Okay, but you should know, okay, it contains some terms, at least two terms. Okay, two terms between VIK, and WK. Okay, then these two terms are missing. Okay, then when you take the expectation on both sides of the equation 12.6, then you will get some equation like this. Okay, so calculation is very straightforward. Okay, then you can define the F bar will be A minus Q Ki Hi will be just some take the expectation of Fik, okay, because the mean of the gamma Ik, so it's Q. Okay. Then next step, if you let I is the same as J, then you want to find the K to minimize the mean square estimation error. Okay. The same I. Here, but I do not like this approach. Okay, so I will not follow this approach. Okay, then I will show you another approach. Okay, let's go directly to here. So here we can again, when we take j to I, then we take expectation on both sides, then you will get a similar equations. Okay, like this one, like 12.7. Then there's one place you need to pay attention. So it's this term. Okay, so this term. Okay, so you have here you have A. Okay, A minus gamma I. So K. So let's forget about I. So KH. Okay, then you have gamma H transpose, so K transpose. Okay, so there's one place. Okay, then we also have, if we denote, okay, that's just P matrix. Okay, this will be PI. Then you have to pay attention about this gamma. Okay, so when I is not same with J, okay, then you have Q squared. Okay, but when, so this is the gamma I, so this is the gamma I. Okay, so let's say when you take expectation, when the gamma I and the gamma J, then you have Q squared. Okay, so when I is not same with J. Okay, but the case is, so when gamma is same with J, okay, then the expectation of gamma I squared, okay, so gamma I squared, okay, it will be Q, okay, not Q squared. Okay, so that one place you have to pay attention. Okay, then why it's Q, not Q squared. Okay, then you can use the definition. Okay, so the expectation of gamma I squared, okay, we know will be the probability. So probability of gamma I equals 1, okay, then times 1 squared, then plus the probability when gamma I equals 0, then times 0 squared. Then now this term is 0. Okay, so 1 squared is 1. Then the probability of gamma I is 1, so it's Q. Okay, so when I is same with J, so the expectation of gamma I squared is Q, not Q squared. Okay, so that's the only place you need to pay attention. Then therefore, okay, here you have the same term, then you need to minus Q squared. Okay, so KHI, KI, HI transpose. Okay, then you have the Q term. Okay, that's the only difference between 12.11 and 12.7. Okay, there's the only place you need to pay attention. Then we want to minimize, because in the book it said we want to minimize the expectation of EI, okay, the EI transpose. Then it will be, it doesn't make sense because this is a matrix, okay? So you never know how to minimize a matrix, okay? Therefore, okay, so the right way to say it, we want to minimize the trace of the matrix, okay? Not the matrix itself, okay? We want to minimize the trace, okay? Then we can take the trace on both sides, okay? If we take the trace on both sides of the equation, okay, then we can take the partial derivative, okay. So here you will see, so this is the quadratic equation, okay, in terms of K, the matrix K, okay. Then the K transpose, then the coefficient is positive, okay. Then we know when we minimize this, the trace of PIK, okay, the partial Ki, so it will minimize, okay, the mean square error, okay. Then there are a few terms, okay. There are many terms that are independent of K. Then from here, then you should have a term. Let's go back to the definition here. Then you should have the A term, okay, then times the transpose of this part, okay. Then you should have one term will be the minus, okay, that's A, then P, okay, then the Fi transpose will be this part, okay. Let's put the Q in front, okay. Then you have H transpose and K transpose, okay. Then you get H transpose, then K transpose, okay. Then have to put trace here. Then you take partial that to partial K, okay. Then you get a term like this, okay. So minus Q, that will be HP, then A transpose, okay. Okay, you have one subterm, then you have another term, okay. Another term will be the transpose of this term, okay. It's because you have this Q, K, H HI, then you have A transpose, okay. Then you have another similar term will be the partial, the trace, okay, trace minus the Q, okay, be K H P A transpose, okay. Then you take partial K, then you have exactly the same term, okay. Then Q H P A transpose, okay. So you exactly have the same term, okay. So let me erase it, okay. Then put a 2 here, okay, in the first equation, okay. So let's put 2 here, okay. So this 2. Then we know this one term here, okay, will be the partial, it's a trace. So the Q, so K H P H transpose is a K transpose, okay. So partial trace partial k, okay? Then in this case, so the result will be 2 times q h p, the p h transpose, and k transpose, okay? Then you have another term here. It will be partial trace, then q k r k transpose, okay? Then partial k, then here you have 2 times q r k transpose, okay? Then there's another place, okay? So you have the k here is in the f bar, okay? So here you have the f bar. So similar to that case, okay? Then you have the partial, okay? Then the trace, okay? So here, because if you see the definition, you have minus q k h I, okay? So here you have minus q k h I, therefore have q transpose epsilon, okay? Then k h, then you have the sum, okay? And the sum, so A transpose, you take partial k, then there's another term, therefore you know there are 2 times, okay? Then there's another term, let's take them together, okay? Let's multiply 2 here. You have 2, there'll be q transpose, so epsilon, okay? So h, then the sum, then A transpose, okay? Then you let, okay, this to be 0, okay? Then you collect the term. You see these 2 terms, okay? It contains k transpose, okay? So when we have the equal, we can divide the 2, then all the 2, it doesn't matter the 2 coefficient, okay? The 2 is gone. Okay. Then we move the k to one side. Okay. Then you get so q h p h transpose. Okay. Then plus q times r. Okay. Then k transpose. Okay. You see here it defined as m. Okay. Then we can write as m. So it will be m, and k transpose will be equal to these 2 terms. Okay, so it'll be, if we take 1 q out, then it will be, okay, maybe let me write here. So m k transpose. If we take 1 q out, okay, there'll be h p a, we can take h outside, okay, h, then p, okay, so h, then p, we have a transpose, we take a transpose here, then here you can, it will be minus, we take 1q, 1h, have q epsilon, then the sum, okay, then the k, okay, transpose, okay, will be the m inverse, so QH, so P minus Q epsilon sum, okay? Then A transpose, then you take the transpose, then you get K, okay? Then you exactly have the result here, okay? That will be the Q, A, then here, the P, then you can switch the sign. So here you have PI minus PIS. So here you have PIS minus PI, okay? Then have H and M transpose, okay? Then you exactly get the same result here, okay? Okay, so that is the set the optimal estimator gain, okay? So as I mentioned, okay, it doesn't mean the estimator is optimal, okay? So here, it only means the K is optimal, okay? It doesn't mean the estimator is optimal. Then when epsilon is 0, means there's no consensus term, okay? You only use the first two terms, okay? No third term. Then in this case, then you have this equation, okay? Just let the epsilon be 0, okay? Then this term is gone, okay? Then have QA, P, okay? H transpose, M, K transpose, okay? Then the P, okay? You just let the epsilon part be 0, okay? So all these terms will be gone, okay? Okay, you get this term, okay? The FP, F transpose, then you have the Q, capital Q, okay? Then Q1 minus Q, then KP, KH, okay? Then again, here it's sub-optimal, okay? It's not optimal, okay? It's not optimal, okay? So even you do not include the consensus term, okay? Like even for a single sensor case, okay? When you have this random variable, then you choose this filter, okay? If you choose this filter here, okay? When you choose this filter, even without this term, if you choose this filter, okay? Then you calculate the gain in this way, okay? Then the K not optimal, okay? So it's sub-optimal gain,